Hello, in this lecture we'll answer on two questions. In the first question, we find out the area of this green shape that is inside square ABCD. And in the second question, we find out the area of this green shape that is inside quarter circle AOB. So we start with the first question. In the drawing, we have square ABCD. We know that line segment PQ equals to 2 units. Line segment PQ equals to 2 units in its length. This is line segment QC that is equals to 3 units. This is angle PQC that is a right angle. Again, our mission is to find out the area of this green shape. That is actually the area of quadrilateral PDCQ. So first of all, we know that all the angles inside any square are right angles. So those two angles are all right angles. So okay, this is a right angle. This is also a right angle. This angle is a right angle. And finally, this is also a right angle. We know that all the sides of any square, they are equal to each other. So we will define one side of this square as A. Therefore, we get that AB equals to BC equals to CD equals to DA equals to A. So this is side AD. That is equals to A units in its length. This is side AD, this is also equals to A units. This is side DC that is equals to A units, and side BC also equals to A units. In the next step, we define the length of this line segment BQ as X. So what is the length of this line segment AQ? From the drawing, it is very easy to see that AQ equals to AB minus QB. So AQ equals to AB minus QB. So AQ equals to AB, that is A, minus QB, that is X. So in total, AQ equals to A minus X units. AQ equals to A minus X. This is line segment AQ that is equal to A minus X units in its length. In the next step, we define the size of this angle that is actually angle QCB as alpha. So in the right triangle QCB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. We note that AB is one side of square ABCD, and therefore it is absolutely a straight line. So AB is a straight line. So if we focus on this side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle that is 90 degrees minus alpha, plus this angle that is 90 degrees, plus this missing angle. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. Therefore, this first missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles on one side of this straight line AB. So in the right triangle APQ, this right angle APQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, I'll copy this right triangle APQ and this right triangle QBC in the new page, and we'll prove that those two right triangles are similar to each other according to angle similarity rule. So actually, those are the two right triangles that are coming from the original drawing. This is the right triangle APQ, and this is the right triangle QBC. So in the next step, we'll prove that those two right triangles are similar to each other according to angle similarity rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. So okay, this is angle AQP. In the right triangle APQ, and it is equal to this angle, this is actually angle BCQ. In the right triangle QBC. But again, angle AQP equals to angle BCQ equals to alpha, they're both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle QAP in the right triangle APQ, and it is equal to this angle. This is actually angle QBC in the right triangle BQC. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees from alpha, therefore they are equal to each other. So actually this is angle APQ in the right triangle APQ, and it is equal to this angle, it is actually angle BQC in the right triangle BCQ. So they are both equal to 90 degrees from alpha, therefore they are equal to each other. So actually prove that all the figures in this right triangle APQ correspondingly equal to all the figures of this right triangle QBC. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. Actually proved that this right triangle APQ is similar, this is the sign of similar to this right triangle QBC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of this right triangle APQ over side QB of this right triangle QBC is equal to side AQ of this right triangle APQ over side BC of this right triangle QBC, and it is also equal to side PQ of the right triangle APQ over side QC of this right triangle QBC. And again, I actually found out that according to equation 1, AP over QB equals to AQ over BC equals to PQ over QC. AP is the missing side, so we leave it as it is. Over QB, QB is X, and it is equals to AQ, AQ is A minus X, over BC, BC is A, and it is also equals to PQ, that is 2, over QC, that is 3. So in total, according to equation 1, we also found out that AP over X equals to A minus X over A equals to 2/3. So here, those two expressions are equal to each other. Therefore, we get equation 1 from those two expressions that are equal to each other. So according to equation 1, AP over X equals to 2/3. Here we multiply the equation by X, and we get that according to equation 1, AP equals to 2/3 times X. Actually, we found out that according to equation 1, AP equals to 2/3 X. So here, those two expressions are also equal to each other, so we create equation 2 from those two expressions that are equal to each other. And we get that according to equation 2, so according to equation 2, A minus X over A equals to 2/3. Here we cross multiply this equation 2, and finally get that according to this equation 2, 3 times A minus X equals to 2A. Here we'll open the brackets of this side of equation 2, and we get that according to equation 2, 3A minus 3X equals to 2A. So here we subtract 2A from this equation 2, and finally get that According to equation 2, 3a minus 2a is a, so a minus 3x equals to 0. Here we add 3x to this equation 2, and finally get that according to equation 2, a equals to 3x. But again, I should find out that according to equation 2, a equals to 3x. In the next step, I'll copy the right triangle QBC in the new page, and we will implement the Pythagoras theorem. This right triangle QBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here, by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle QBC that I covered from the original drawing. According to the Pythagoras theorem, this right triangle QBC, QC squared, that is the square of the hypotenuse, equals to QB squared plus BC squared. So I write it down. This will be equation 3. So according to equation 3, QC squared, that is the square of the hypotenuse, QC squared equals to QB squared plus BC squared. The hypotenuse QC equals to 3, therefore QC squared is 3 squared, that is 9, and it is equals to QB squared. QB is x, therefore QB squared is x squared plus BC squared. BC is a, therefore BC squared is a squared. So in total, actually, according to equation 3, we found out that 9 equals to x squared plus a squared. This is according to equation 3, while according to equation 2, we have already found out that a equals to 3x. Equals to 3x. If a equals to 3x, it means that a squared must be equal to 3x squared. Therefore, we can substitute a squared in this equation 3, by 3x squared for this equation 2. We'll do it now, and we get that according to equation 3, according to equation 3, 9 equals to x squared plus a squared. A squared is 3x squared, according to equation 2. So in total, we found out that according to equation 3, 9 equals to x squared plus 3x squared. 3x squared is 9x squared. So in total, we found out that according to equation 3, 9 equals to x squared plus 9x squared is 10x squared. So according to equation 3, we found out that 9 equals to 10x squared. Here we divide this equation 3 by 10, and finally get that according to equation 3, x equals to 9/10. So here we take a root out of this equation, and finally get that x equals to the square root of 9, that is 3, over square root of 10. In total, we should find out that x equals to 3 over square root of 10 units in its del. According to equation 2, a equals to 3x. A equals to 3x. So a equals to 3 times x. And x is 3 times square root of 10. So it is 3 times 3 for square root of 10. So in total a equals to 3 times 3, that is 9 over square root of 10 units in its length. And again, a equals to 9 over square root of 10 units in its length. That is to say, the length of one side of square ABCD, that is A, is equals to 9 over square root of 10 units in its length. This is side DC of square ABCD, that is equals to A, and A equals to 9 over square root of 10 units in its length. What is the length of AP? According to equation 1, we shall find out that AP equals to 2/3 x. Repeat again. According to equation 1, we have already found out that AP equals to 2/3 x. So AP equals to 2/3 x, and x is 3 over square root of 10. So AP in total equals, here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. So in total AP equals to 2 over square root of 10 units in its length. And again, AP equals to 2 over square root of 10 units in its length. So okay, this is line segment AP. This is equals to 2 over square root of 10 units in its length. What is the length of line segment PD? From the drawing, it is very easy to see that PD equals to AD minus AP. So write it down. PD equals to AD minus AP. Again, PD equals to AD minus AP. So PD in total equals to AD. AD is A, that is 9 over square root of 10. Minus AP. Just like I found out that AP equals to 2 over square root of 10. So in total, PD equals to 9 over square root of 10 minus 2 over square root of 10. That is actually 7 over square root of 10 units in its length. So the non-PD equals to 7 over square root of 10 units in its length. In the next step, we join points P and C together by a straight line. By joining points P and C, we can do 2 right angles, the right angle PDC and the right angle QPC. Actually, the green shape consists of the two right angles, the right angle PDC and the right angle PQC. And therefore, the area of the green shape must be equal to the area of the two components that the green shape consists of. That is to say, the area of the green shape must be equal to the area of the right angle PDC plus the area of this right angle PQC. So write it down. The area that we are looking for, that is the area of the green shape, must be equal to the area of this right triangle PDC plus the area of the right triangle, this right triangle PQC. Repeat again, I should find out that in total the area of the green shape is equal to the area of the right triangle PDC plus the area of the right triangle PQC. So the area of the green shape equals to the area of the right triangle PDC. The area of the right triangle PDC is equals to the base of the right triangle PDC, that is PD, times the height, that is DC, over 2. Repeat again, the area of the right triangle PDC is equal to the base of the right triangle, that is PD, times the height, that is DC, over 2. Plus the area of this right triangle PQC. The area of the right triangle PQC equals to the base of the right triangle, that is PQ, times the height, that is QC, over 2. Repeat again, the area of the right triangle PQC equals to the base, that is PQ, times the height of the base, that is QC, over 2. So in total, the area of the right triangle PDC, the area of the right triangle PDC equals to PD. PD is 7 over square root of 10, you can see here. Times DC. DC is 8, that is 9 over square root of 10, divided by 2. So again, the area of the right triangle PDC in total equals to PD, that is 7 over square root of 10, times DC, that is 9 over square root of 10, divided by 2. Plus the area of the right triangle PQC. The area of the right triangle PQC equals to PQ, that is 2, times QC, that is 3, divided by 2. Again, the area of the right triangle PQC equals to 2 times 3 over 2. So in total, the area of the green shape equals to, here, the value of this expression is 7 times 9 is 63, over square root of 10 times square root of 10 is 10, divided by 2. Plus 2 times 3 over 2 is 3. Those 2 we get cancelled and left only with 3. So in total, the area of the green shape equals to 63 over 10 over 2 is 63 over 10 times 2, that is 63 over 20, so 10 times 2 is 20, plus 3. So here we multiply 3 by 20, and then we divide it by 20 in order to overcome part of this number, and we get that the area of the green shape in total equals to 63, and 3 times 20 is 60, divided by 20. So in total, the area of the green shape equals to 63 plus 60 is 123 over 20. In terms of numbers, it is equals to 6.15 square units. So repeat again, I actually found out that the area of this green shape is equal to either 123 over 20 square units, so in terms of numbers, the area of this green shape is equal to 6.15 square units, okay? So we finish with the first question. In the next step, I present to you the second question and we will solve it. Our mission in the second question is to find out the area of this green shape. So in the drawing we have a quarter circle AOB, This is angle AOB, that is the right angle. Those two angles are also right angles. OB equals to 5. Therefore, the radius of this quarter circle equals to 5. In addition, we know that arc AP equals to arc PQ equals to arc QB. Again, arc AP equals to arc PQ equals to arc QB. Again, our mission is to find out the area of this ring shape. So because of the fact that arc AP equals to arc PQ equals to arc QB equals to arc QB, here we can implement rule 20. So click quickly on rule 20. According to rule 20, in front of equal arcs, there are equal central angles. Again, in front of equal arcs, there are equal central angles. So in the drawing, we have a circle, and inside the circle, we have arc AB that is equal to arc CD. Again, arc AB equals to arc CD. And according to this rule 20, in front of equal arcs, there are equal angles. There are equal central angles. So those two arcs are equal to each other, and therefore in front of those two equal arcs, there must be equal central angles. Those two central angles are located in front of those two equal arcs, and therefore they must be equal to each other. That is to say, according to rule 20, central angle alpha equals to central angle beta, or alpha equals to beta. So we can actually implement rule 20 in our drawing. Why? Because in our drawing, arc AP equals to arc PQ equals to arc QB. So in the next step, we join points O and Q together by a straight line. And we join points O and P together by a straight line. So, according to rule 20, because of the fact that arc AP equals to arc PQ equals to arc QB, in front of those two three equal arcs, there must be equal central angles. So, those three central angles, they are all located in front of those two equal arcs, therefore they must be equal to each other. So if we define the size of this central angle AOP is x, then the size of central angle POQ must be also equal to x, and the size of this central angle QOB must be also equal to x degrees in its size. Okay? It is very clear from the drawing that the sum of those two angles is the size of angle AOB. That is to say, x plus x plus x, that is 3x, is equal to angle AOB. And we know that angle AOB equals to 90 degrees. And therefore, in total, we found out that 3x equals to 90 degrees. So I write it down. From the drawing, it is very clear that 3x, that is the sum of those three angles, is equal to angle AOB, and angle AOB equals to 90 degrees. So 3x equals to 90 degrees in total. 3x equals to 90 degrees. Here we divide this equation by 3, and finally we get that the missing angle x equals to 90 degrees over 3, that is 30 degrees. So the missing central angle AOP, that is x, is equals to 30 degrees in its size. Central angle POQ also equals to x, and x equals to 30 degrees in size, and central angle QOB is also equals to x, that is equals to 30 degrees in its size, according to rule 20, of course. So in the right triangle MOP, this angle equals to 90 degrees, this angle equals to 30 degrees, therefore this third missing angle must be equal to 60 degrees in its size. Likewise, in the right triangle NOQ, this angle equals to 90 degrees, this big angle equals to 30 degrees plus 30 degrees, that is 60 degrees, and therefore this third missing angle must be equal to 30 degrees in its size according to the rule that I mentioned a lot of times, that the sum of the angles in any triangle is equal to 180 degrees. Therefore this third missing angle must be equal to 30 degrees in its size. So in the next step I'll copy this right triangle MOP and this right triangle MQO in a new page, and we will prove that those two right triangles can go into each other according to angle side angle rule. So actually, those are the two right triangles MPO and NQO that are copied from the original drawing. So in the next step, we will prove that those two right triangles can go into each other according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles this is angle NOQ, is equals to 60 degrees in its size. Angle NOQ equals to 60 degrees in its size. And therefore this angle NQO equals to 30 degrees in its size. So, repeat again. Those two angles are both equal to 30 degrees and therefore they are equal to each other. So this is angle MOP in the right triangle MPO, and it is equal to this angle, that is actually angle NQO in the right triangle QNO. They are both equal to 30 degrees and therefore they are equal to each other. In addition, those two angles are both equal to 60 degrees and therefore they are equal to each other. So actually this is angle MPO in the right triangle MOP, and it is equal to this angle, that's actually angle NOQ in the right triangle NQO. They are both equal to 60 degrees and therefore they are equal to each other. And finally, side PO equals to side QO. They are both the radii of the circle and therefore they are equal to each other. So I write it down. Side PO in the right triangle MPO is equal to side QO in the right triangle NQO. Now both the radius of the circle that is equal to 5 and therefore they are equal to each other. Repeat again. This is my segment PO. This is actually the radius of this quarter circle. The radius of this quarter circle equals to 5 units in its length. QO is also the radius of the quarter circle is equal to 5. So actually found out that in the right triangle NPO we have those two angles, and the side that included between those two angles, that is side PO, in this right triangle NPO, are correspondingly equal to those two angles, and the side that included between those two angles, that is side QO in the right triangle NQO. And therefore those two right triangles can go into each other according to angle side angle rule. So I'll write it down. So I found out that this right triangle MPO congruent, this is the sign of congruent to the right triangle NQO according to angle side angle rule. So repeat again. Those two angles and the side that is included between those two angles, that is side PO, in this right triangle NPO, are correspondingly equal to those two angles, and the side that is included between those two angles, that is side QO, in the right triangle NQO. And therefore those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we derive that they have also the same areas. Okay? That is to say, we derive that the area of this right triangle MPO is equal to the area of this right triangle NQO. Repeat again. Because of the fact that those two right triangles can go into each other, we derive that they have also the same areas. That is to say, the area of the right triangle MPO is equal to the area of the right triangle NQO. The right triangle MPO consists of two components. That is to say, it consists of this quadrilateral MP and S. So the right triangle MPO consists of this green quadrilateral MP and S, and also it consists of this small right triangle NSO. And therefore the area of this right triangle MPO must be equal to the area of the green quadrilateral MP and S plus the area of this small right triangle NSO. So write it down. The area of the right triangle MPO is equal to the area of quadrilateral MP and S plus the area of this small right triangle NSO. Repeat again. Because of the fact that the right triangle MPO consists of exactly two components, that is to say, it consists of quadrilateral MP and S, and it also consists of the right small triangle NSO. And therefore the area of the right triangle MPO must be equal to the sum of the areas of the two components that it consists. That is to say, it is equal to the area of quadrilateral MP and S plus the area of the small right triangle NSO. And according to equation 1, the area of triangle MPO equals to the area of triangle NQO. This is the area of triangle NQO. So the area of this triangle, the right triangle NQO, it consists of two components. It consists of the area of this right triangle NSO plus the area of this right triangle SQO. That is to say, the big right triangle NOQ consists of two triangles. Consists exactly two triangles, and therefore the area of the right triangle NQO must be equal to the sum of the areas of the two components that it consists of. That is to say, it must be equal to the area of this right triangle NSO plus the area of this triangle SOQ. Repeat again, because of the fact that this right triangle NQO consists of two small triangles, exactly two small triangles, therefore the area of the big triangle NQO must be equal to the sum of the areas of the two small triangles that it consists of. That is to say, the area of the right triangle NQO must be equal to the area of the small right triangle NSO plus the area of triangle SQO. So here we have the area of triangle NSO on both sides of the equation, so it will be cancelled. If we subtract the area of triangle NSO from both sides of the equation, it will be cancelled, and we left only with the area of triangle of quadrilateral MPNS that is equal to the area of triangle SOQ. So in total we found out that the area of this green quadrilateral MNSP is equal to the area of this triangle SQO. So if we define the area of this quadrilateral MNSP as A, then the area of this triangle SOQ must be also equal to A, because they are equal to each other according to equation 1. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total equals to the area of this quadrilateral MNSP plus the area of this green shape PSQ. So I write it down. The area of the green shape in total equals to the area of quadrilateral MNSP that we defined as A plus the area of this green shape PSQ. So repeat again, we should find out the area of this green shape in total equals to the area of the green quadrilateral MNSP plus the area of the green shape PSQ. But we already found out that the area of quadrilateral MNSP equals to the area of triangle SOQ. Therefore, we can substitute the area of quadrilateral MNSP by the area of triangle SOQ. We do it now, and we get that the area of the green shape in total is equal to, again, the area of quadrilateral MNSP is equal to the area of triangle SOQ. Therefore, we substitute the area of quadrilateral MNSP by the area of triangle SOQ plus the area of the green shape PSQ. So in total we should find out that the area of the green shape, the area of this green shape equals to the area of triangle SOQ, the area of this white triangle SOQ plus the area of the green shape PSQ. But the sum of the areas of those two components It is equals to exactly to the area of sector POQ. Again, the sum of the areas of triangle SOQ plus the area of this green shape PSQ. In total, it is equals to the area of sector POQ. Okay? It is equal to the area of sector PSQ. So in total, we found out the area of this green shape equals to the area of sector POQ. But again, in total, we found out the area of the green shape equals to the area of sector POQ. So what is the area of sector POQ? Actually, the area of any sector equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector over 360 degrees. So write it down. The area of this sector POQ must be equal to pi r squared, that is the area of the circle that contains this sector POQ, times the angle between the legs of this sector, that's actually 30 degrees, over 360 degrees. I repeat again, we shall find out that in total, the area of the green shape equals to pi r squared times 30 degrees over 360 degrees. We know that the radius r of this quarter circle equals to 5. Therefore, r squared is 5 squared, that is 25. So pi r squared is 25 pi. 30 degrees over 360 degrees is 1 over 12. So in total, we shall find out the area of this green shape equals to either 25 pi over 12 square units, or in terms of numbers, the area of this green shape equals to 6.545 square units. 6.545 square units. So repeat again, we shall find out in total the area of this green shape equals to either 25 pi over 12 square units, or in terms of numbers, the area of this green shape equals to 6.545 square units. So finish with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. The first question, our mission is to find out the area of this green shape. So in the drawing we have square ABCD. We know that this angle PQC, that is the right angle. We know that this is side PQ, that is equal to 2 units in its length. This is side QC, that is equal to 3 units in its length. Again, our mission is to find out the area of this green shape. So first of all, we know that all the angles inside any square are right angles. So those 4 angles are all right angles. We define one side of this square ABCD as A. Therefore, DC equals to CB equals to BC equals to AD equals to A. We define the length of this side QB as X. Therefore, AQ must be equal to AB, that is A, minus QB, that is X. So in total, AQ equals to A minus X. We define this angle as alpha. This angle, so in the right angle, QBC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha, because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. AB is one side of square ABCD, therefore it is absolutely a straight line. So if we focus on this side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3, that says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle that is 90 degrees minus alpha, plus this angle that is 90 degrees, plus this missing angle. In total, they must be equal to 180 degrees according to rule 3. Therefore, this third missing angle must be equal to alpha. So the right angle QAP, this angle equals to alpha, this angle equals to 90 degrees, therefore this third angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I prove it. The right triangle APQ, this right triangle APQ, this right triangle QBC in a new page, and we prove that those two right triangles are similar to each other according to angle similarity rule. So those are the two right triangles that are according to the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I shall prove that all the triangles inside this right triangle APQ are corresponding equal to the triangles inside this right triangle QBC. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that they are similar to each other, we derive that the following relationship exists between their sides. We derive that AP over QB equals to AQ over BC equals to PQ over QC. AP is the missing side, so we leave it as it is. QB is X, AQ is A minus X, BC is A, PQ is 2, and QC is 3. So in total, according to the question 1, we actually found out that AP over X equals to A minus X over A, and it is equals to 2/3. Those two expressions are equal to each other, therefore we get equation 1 from those two expressions that are equal to each other. So according to equation 1, AP over X equals to 2/3. Here, because we multiply this equation by X, and finally found out that AP equals to 2/3 X. This is equation 1. Those two expressions are equal to each other, therefore we get equation 2 from those two expressions that are equal to each other. That is to say, according to equation 2, A minus X over A equals to 2/3. Here, of course, multiply this equation and finally found out that 3 times A minus X equals to 2A. We open the brackets on this side of equation 2 and finally found out that 3A minus 3X equals to 2A. Here we subtract 2A from this equation and finally found out that 3A times 2A, 3A minus 2A is A, so A minus 3X equals to 0. We added 3X to this equation and finally found out that A equals to 3X. According to equation 2, A equals to 3X. In the next step, I copied the right triangle QBC in the new page and implemented the Pythagoras theorem on this right triangle QBC. So here, this is the right triangle QBC that I copied from the original domain. According to the Pythagoras theorem, in this right triangle QBC, QC square equals to QB square plus BC square. QC is 3, therefore QC square is 3 squared, this is 9, and it's equal to QB square. QB is X, therefore QB square is X square plus BC square. BC is 8, therefore BC square is A square. So in total, according to equation 3, we found out that 9 equals to X square plus A square. But according to equation 2, A equals to 3X. If A equals to 3X, it means that A square must be equal to 3X squared. Therefore, we can substitute A square in this equation 3, by 3X squared. We did it, and we found out that according to equation 3, 9 equals to X squared plus A squared, and A squared is 3X squared, 3X squared according to equation 2. So in total, we found out that 9 equals to X squared plus 3X squared. So according to equation 3, 9 equals to X squared plus 3X squared. 3x squared is 9x squared. So in total, we found out that 9 equals to x squared plus 9x squared, that is 10x squared. So 9 equals to 10x squared, according to equation 3. Here we divided the equation 3 by 10, and finally found out that x equals to 9 tenths. Here we took out of this equation, and finally found out that x equals to the square root of 9, that is 3, over the square root of 10. This is according to equation 3, but according to equation 2, we found out that a equals to 3x. So a equals to 3, and x is 3 over the square root of 10. So in total, a equals to 3 times 3, that is 9 over the square root of 10. Okay, again, we should have found out that a equals to 9 over the square root of 10 units instead. So okay, this is side DC, that is equal to a, and a equals to 9 over the square root of 10 units in its length. Now we have to find out what is the length of AP. According to equation 1, AP equals to 2/3 x, so AP equals to 2/3 x, and x is 3 over the square root of 10. Here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled, so after we cancel We found out that AP in total equals to 2 over square root of 10. And again, AP equals to 2 over square root of 10 units in its length. What is the length of PD? From the drawing, it is very easy to see that PD equals to AD minus AP. Again, PD equals to AD minus AP. So PD in total equals to AD, that is A, and A equals to 9 over square root of 10, minus AP, that is 2 over square root of 10. So PD equals to 9 over square root of 10 minus 2 over square root of 10, that is 7 over square root of 10. Again, PD equals in total to 7 over square root of 10 units in its length. In the next step, we join points P and C together by third line. By doing this construction, we're going to do two right triangles because of the fact that the green shape consists exactly those two right triangles. It means that the area of the green shape must be equal to the sum of the areas of those two right triangles. That is to say, the area of the green shape must be equal in total to the area of the right green triangle PDC plus the area of the right green triangle PQC. So the area of the green shape equals to the area of the right triangle PDC. And the area of the right triangle PDC equals to PD, this is the base of the triangle, times DC, that is height, over 2. Plus the area of this right triangle PQC, that is equals to PQ, that is the base, times QC, that is the height, divided by 2. Again, it is PQ, that is the base, times QC, that is the height, over 2. PD is 7 over square root of 10, TC is 8, that is 9 over square root of 10, divided by 2. PQ is 2, PC is 3, divided by 2. Here 7 times 9 is 63, square root of 10 times square root of 10 is 10, divided by 2. Plus, here 2 we get cancelled, and we left only with 3. So in total, we shall find out that the area of the green shape equals to 63 over 10 over 2 plus 3. 63 over 10 over 2 equals to 63 over 10 times 2, that is 20. So this expression equals in total to 63 over 20 plus 3. Here we multiplied 3 by 20 and then we divided by 20 in order to have a common factor of this number. In total, we found out that the area of the green shape equals to 63, and 3 times 20 is 60 divided by 20. 63 plus 60 is 123 divided by 20. So if we found out that the area of this green shape equals to either 123 over 20 square units, so in terms of numbers, the area of this green shape equals to 6.15 square units. We finish with the first question. In the next step, I presented to you the second question, and we solve the second question. Our mission in the second question is to find out the area of this green shape. So, in the drawing, we have total second AOB. This is again AOB, this is right angle, those two angles are also right angles. We know that arc AP equals to arc PQ equals to arc QB, and also know that OB equals to 5. That is to say, the radius of this quarter circle equals to 5. Again, our mission is to find out the area of this green shape. So here we can implement rule 20, I'll repeat quickly rule 20. According to rule 20, in front of equal arcs, there are equal center angles. In the drawing we have a circle, and we know that arc AB equals to arc CD, and therefore according to this rule, rule 20, in front of those two equal arcs, that is to say AB and CD, we have equal center angles. That is to say, center angle alpha equals to center angle beta, or alpha equals to beta. So we can actually implement rule 20 in our drawing. First of all, we join points O and P together by a third line, we join points O and Q together by a third line. So we know that arc AP equals to arc PQ equals to arc QB, and according to rule 20, in front of those two equal arcs, we have those three center angles that must be also equal to each other. So this angle is x, this angle must be also equal to x, and this angle must be also equal to x according to rule 20. So x plus x plus x equals to angle AOB. From one side, angle AOB equals to 3x in its size. From the other side, we know that angle AOB is a right angle. Therefore, in total, we found out that 3x equals to 90 degrees. We divide this equation by 3 and find out that x equals to 30 degrees. Center angle AOB equals to 30 degrees, center angle POQ equals to 30 degrees, and center angle QOB also equals to 30 degrees in its size. In the right angle MPO, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this third angle must be equal to 60 degrees in its size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the right triangle NOQ, this angle equals to 60 degrees, this angle equals to 90 degrees, and therefore this third angle must be equal to 30 degrees in its size. In the next step, I copy this right triangle NOQ and this right triangle MPO in an equation. We prove that those two right triangles can go into each other according to angle side angle rule. So those are the two right triangles that I copied from the original drawing. So why those two right triangles can go into each other? First of all, those two angles are both equal to 30 degrees and therefore they are equal to each other. In addition, those two angles are both equal to 60 degrees and therefore they are equal to each other. And finally, side PO equals to side QO. They are both the radii of the circle and therefore they are equal to each other. So I can prove that those two right angles can go into each other according to angle side angle rule. We have those two angles inside that included between those two angles, that is side PO. In this side angle MPO corresponding equals to those two angles, and the side that included between those two angles, that is side QO, in the right angle MQO. And therefore those two right angles can go into each other according to angle side angle rule. From the fact that those two right angles can go into each other, we will derive that they have also the same areas. That is to say, we will derive that they are on the right angle MPO equals to they are on the right angle NQO because of the fact that they can go into each other. But the right angle MPO consists of this green quadrilateral MPSN, and it also consists of this small right angle NSO. And therefore, the area of the right angle MPO must be equal to the area of quadrilateral MNSP plus the area of this right angle NSO. So repeat again, because of the fact that the right triangle MPO consists of exactly those two components, it means that the area of the right triangle MPO must be equal to the area of quadrilateral MPNS plus the area of the right small triangle NSO. And we know that the area of triangle MPO equals to the area of triangle NQO. So this is the triangle NQO. Triangle NQO consists of exactly those right triangle NSO and this triangle SOQ. And therefore, the area of this right triangle NQO must be equal to the area of this small right triangle NSO plus the area of this triangle SQO. Repeat again. The area of the right triangle NQO must be equal to the area of the right small triangle NSO plus the area of triangle SOQ. Because of the fact that triangle NQO consists of exactly those two components. We have the right triangle NSO on both sides of the equation, so it will get cancelled, and we're left only with the area of quadrilateral MP and S that equals to the area of triangle SOQ. That is to say, the area of this quadrilateral MPSN is equals to this area of the right triangle OQS. So if the area of this right triangle is 8, then the area of this triangle, if the area of this quadrilateral MPSN is 8, then the area of this right triangle SQO must be also equal to 8 because they are equal to each other according to rule 1. Our mission is to find out the area of this green shape, the area of this green shape. So what is the area of this green shape? From the drawing, it is very easy to see that the area of the green shape equals to the area of this green quadrilateral MNSP plus the area of this shape PQS. Repeat again, the area of the green shape in total equals to the area of quadrilateral MNSP plus the area of shape PSQ. But we already found out that the area of this quadrilateral MNSP equals to the area of this right triangle NSQ, the area of this triangle, right triangle SOQ. Therefore, we can substitute the area of this green quadrilateral MNSP by the area of this triangle SOQ. So we did it. We substituted the area of this quadrilateral MNSP by the area of triangle SOQ because they are equal to each other, and we also plus the area of the green shape PSQ. So in total we should find out that the area of this green shape equals to the area of this white triangle SOQ plus the area of this green shape. But the sum of the areas of those two components equals to the area of sector POQ. Again, the sum of the areas of those white triangle SOQ plus this green shape PSQ is exactly equal to the area of sector POQ. So again, the area of the white triangle SOQ plus the area of the green shape PSQ equals exactly to the area of sector PQO. So what is the area of sector PQO? The area of sector PQO equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees over 360 degrees. I repeat again, the area of sector PQS equals to pi r squared times the angle between the legs of the sector, that is 30 degrees over 360 degrees. R, this is the radius of this quarter circle, is 5, therefore r squared is 5 squared, that is 25. So pi r squared is 25 pi, pi r squared is 25 pi, and 30 degrees over 360 degrees is 1 over 12. So in total we shall find out that the area of this green shape equals to either 25 pi over 12 square units, or in terms of numbers, the area of this green shape is equal to 6.545 square units. Okay, thank you very much.